Okay.
Okay, so we welcome back to the last session of today. So we'll have a set of 3 short talks. So the first is Arhum Ansari, who will tell us about inflationary non-Gaussianities in alpha vacua. Okay, so go on, please. Thank you.
Yeah, so thank you, Suvrat. And I would like to thank the organizers for giving me the opportunity to talk about my work here. As Suvrat said, I'm going to talk about inflationary non-Gaussianities in alpha vacua and consistency with conformal symmetry. And this work is done in collaboration with Nilay Kundu, Prateek Divakar, Pinak, and my supervisor Sachin Jain at ICTS Pune. Okay, so let me begin by just asking the timeless question that how did the universe begin? We are not at all quite there to have a precise answer to this question. However, the earliest observable that we have is the CMB, whose map looks something like this. So so one can say that understanding this picture to the minute details is of utmost importance in our understanding of the physics of the universe. So let me just state what we do know about the universe is that so there is ample evidence that suggests that there was a period of accelerated expansion, which is called inflation. And during this period, the space-time of the universe was very close to being de Sitter. Now, the fluctuations on the CMB are often associated with these correlation function of quantum fluctuations in the vacuum during inflation. So this is how you generate these fluctuations theoretically, at least. So that's the current framework. So now one should ask that, okay, if you are going to compute correlation functions, then what was the initial state in which you're going to compute them? So the 2 common choices that you will find in the literature is the Bunch-Davies vacuum, which is the most natural choice, and then there is the alpha vacuum. So alpha vacuum is just a 1 parameter family of vacua, which are de Sitter invariant, and Bunch-Davies is just 1 point in this family. So the objective of this project was twofold. One was to study the structure of 4-point function in alpha vacuum. And the motivation to do that was that people had found an interesting structure at the 3-point level in alpha vacua just from theory. So it looks something like this. If you have a 3-point function alpha vacua, you can just write in terms of the Bunch-Davies answer with some flips of the momenta, actually mods of the momenta. Now people have also given some CFT interpretation to this formula. So that's also interesting. So these were the reasons that we wanted to see whether some interesting structure is there at 4-point function as well. And we found yes, indeed there is. So the second reason was to study inflationary word identities between 3 and 4-point function. So this I'm going to talk about. So usually you get so through symmetries you get certain relations between n-point functions and n plus 1-point functions. So what was shown in around 2016 by Trivedi and group that the word identity between 2 and 3-point function actually fails. It does not hold. But we have found that it actually works out between 3 and 4-point function. So I'm going to talk about that in a minute. Okay, so let me just give a 1-minute review of what we mean when we say alpha vacuum. So if you try to quantize the massless field in de Sitter space, you will have a typical mode expansion which will look something like this, where the mode function is given here, which you can choose to be satisfying the Bunch-Davies boundary condition, and you'll end up with this mode function. However, the equation of motion allows for 2 linearly independent solutions, and you can take a linear combination of them and also define another mode function. What this does is that it just changes the vacuum state of your solution. So the mode expansion corresponding to this and this are 2 different vacua whose mode functions are given like this. Now to satisfy the normalization condition, you obviously need to have these C1 and C2 to satisfy a condition which is a normalization condition. Now one particular parameterization which satisfies the de Sitter, all the de Sitter symmetries is this shown here, and for the purpose of this talk, I'll always work with beta to be 0. I mean, there is a rigorous argument that that people have shown that for it to be invariant under global de Sitter, this has to be 0, but that's not important. So for me, it will always be 0. So this is going to be my mode functions, and which are parameterized by this parameter alpha. So if you want to write this vacuum state for this mode function in terms of the old or the Bunch-Davies mode function, it will look something like this. It's like a squeeze state in terms of the Bunch-Davies creation annihilation operators. Okay, so that's what defines for me the alpha vacuum. So now the another ingredient that goes into the calculation is the wave function. So let me just quickly go through this. So let's say you want to compute the expectation value of some operator O at certain time t in the vacuum state, which I've denoted here by omega. So you can insert some complete field eigenstates in between, and you'll get an expression like this. So what defines the wave function is these transition amplitudes. Now you can write these transition amplitudes as some sort of path integral with appropriate boundary condition, and these boundary conditions will ultimately determine what initial state you're going to work with. So here there is a pictorial depiction. So you start with something in the past at -infinity, and then you go up to that time, and you say that at that time the field value takes the value phi. So, and then to get the correlation function, you integrate over all phi's. Okay. So okay, you can show that okay in momentum space your wave function will look something like this. You have these field perturbations multiplying some quantity which I am denoting by psi n. So these are what are known as wave function coefficients, which is going to be probably the topic of some of the talks later in the workshop. Okay, now let's say I give you all these wave function coefficients. What can you do with them is that you can compute these correlation functions of the fields. So now let's say I replace this O with some 4 fields, then I can write the correlation function in terms of the wave function coefficients entirely. So you can see this, there's a first term that depends on psi 4, and there is another term which is a product of 2 psi 3s. This is going to be important, that's why I'm showing it. Okay, now just a quick philosophy of why you have these inflationary word identities. So wave function being a boundary quantity must be reparameterization invariance of bulk. So if you impose that on the wave function and say that specifically for dilatations and SCTs, your wave function is invariant, you'll see that it relates some psi n plus 1 with psi n's. Now you can convert those relations to correlation functions, and you'll get something like
the
this.
alpha vacuum you still define by taking the wave function and multiplying with that coherent state. Is that the definition, or what's the path integral definition of the alpha vacuum?
Yes, so you replace this omega with the alpha. So which basically means in the past you change the boundary conditions.
I see.
Okay, so you get these warranties. So I was saying that okay, warranties relate psi n plus 1 with psi n's, but you can convert into correlation functions, and it will look something like this. So you can see on the right hand side you have a 4-point function, and the left hand side you have 3-point function. Now, so an analog of this for 2 versus 3 is what is commonly known as the Malasinus consistency relation in the literature, and this is what was shown in the earlier paper to not hold for alpha Vacua. Okay. Yeah, so now without going into the details, I'll just show the results because expressions are not that important. So if you just brute force compute these correlation function, you will get these 3 contributions. As I showed, these 2 are coming from this big psi 4 here, and this one will come from the products of psi 3. Yes.
Sorry, so what does it mean that
Yeah, so interpretation is like it's not very clear right now how to interpret it. So the previous paper interpreted it in this manner, that they computed the effective stress tensor in alpha Vacua and showed that it diverges. So then they argued that because of this divergence, the classical geometry itself changes, and therefore it's no longer de Sitter. So like of course you won't expect Ward entities to hold because it's no longer de Sitter. But now that we have shown that it works for 3 to 4, I don't know how to interpret that result. Okay, so out of these three structures, W and G do not have very illuminating form, but I have shown here the form for R because you can see this R has the same form or very similar as I showed for the 3-point function, that you can just completely write it in terms of the Bunch-Davis answer with some flippings of the mods. Okay, so and then we have found that okay, inflationary ward entities for both dilatations and SCT hold between 3 and 4-point function. Now, interestingly, only the part, only this R part actually contributes to the ward identities, and you can see that only this R part has that sort of structure that I showed you. So both these W and G actually vanish identically when you take this limit. So you see there is a limit of K4 going to 0 on the right hand side. So when you take this limit, both these vanish, only this part. So that's an observation. Then as a cross check for our calculations, we also did the same calculation in informalism, as some of you may know, that there exists a equivalent formalism, in formalism, and we found that both the calculations agree. In particular, you have two contributions coming from in. There is a graviton exchange contribution, there's a contact interaction, and specifically they map to these. There was one more minor calculation that we showed. So this previously people had shown for Bunch-Davis, but we just did it for alpha Vacua for fun, and we found that it works. So the calculation is that if you take the 4-point exact de Sitter, 4-point function in exact de Sitter space, and you take one leg and put it to the background on the inflaton field, you will get the inflationary 3-point function. Now this was shown for Bunch-Davis. We also did it for alpha Vacua and shown that it holds. Yeah, towards the end, I just want to point out that still 2 to 3 ward entity does not work, and it's an open issue. Yeah, with this, I'll just conclude. Thanks.
I mean, inflation is not exactly de Sitter anyway because it has to end.
Yes.
So like.
Yeah, so when I showed the ward entities, they are specifically given for inflationary spacetime. For de Sitter, you won't have any right-hand side. So right-hand side will be 0. One can show that it will be.
That's how you get the correlator.
Yes.
And the fact that you have eta equal to 0 slice, there is a CFT that is independent of alpha vacuum, right? Alpha vacuum.
Exactly, that's independent of alpha. And that's why you expect it to hold, because it's also conformally invariant.
So can you show the identity that doesn't work once, please?
So I do not have it on slide, but you can imagine that there is a differential operator acting on 2-point function, and then on the right hand side there is a 3-point function over a 2-point function. Same thing, K3 going to 0.
So, but the alpha Vacua wave function is conformally invariant, right?
Yes.
But then, I mean, the ward identities of conformal transformation should, maybe the point is this is some scalar scale, it's not really a ward identity, right? Is it really a ward identity that comes from conformal invariance?
So this does come from scaling, that I can tell you, but you can also show that this is also a consequence of some diffeomorphism invariant.
But maybe the point is that you shouldn't think of this theta or whatever it is as a field with a given scaling dimension in the alpha Vacua. Maybe that's all that the point is, right? Let me just say, imagine the case where you switched off all interactions. Then the alpha Vacua is just think of the wave function at late times. It's the Hartle-Hawking wave function multiplied with this coherent state. This alpha k dagger alpha k that you wrote. If you write that alpha k dagger alpha k in field space, it's just like taking the wave function and multiplying it with some other quadratic function that comes from here. Like it's some phi x, right? So that's changing the 2-point function. So it's telling you the 2-point function now doesn't look like 1 over k to the 1 over x minus x to the delta, but looks like that plus this. So because of that, you shouldn't think of this field phi as being a primary operator of a given dimension. And so if you do that, of course, you don't expect that the scaling ward identity will work. Because now the 2-point function is not what it is. So is that all that's happening?
I need to think about this, but yeah, it's an interesting point. Yeah, I can
Okay.
think about this.
Okay, thank you.
Thanks.
Okay, if there are no other questions, then maybe we can thank the speaker.